Hello everyone, welcome to our video today where we're talking about general chemistry, chapter 5, kinetics. And to be honest, I used to think this chapter was more challenging than it really is. I was afraid to go over this chapter, but once I started, doing some practice questions and really understanding the concepts, it was a lot easier than I thought. So let's get into it. All right, so first, we have the most important thing to note in this chapter is the lowercase k is the rate constant. And I say lowercase k because in the next chapter we will see another k. But for this, lowercase k for kinetics is the rate constant. And that number is, the value of that number represents the proportion of probability that a collision will result in a successful reaction. What I mean by that is that a reaction needs to have collision, right, of the particles, but then you also need the proper orientation of the particles, and then you also need the minimum required of activation energy for the reaction to proceed, right? So just because you have weak collisions like that, for some substances that won't be enough. You need to make sure they have enough activation energy as well as the proper orientation. So K, just a couple notes about K, is inversely proportional to the activation energy, inversely proportional to concentration, and is proportional to temperature. So that is important to remember. So for the reaction mechanism, you will have fast steps and slow steps. And in that case, the slow step is what determines the rate of the reaction. That is so important to understand. You can have different, you might see different lines and it'll say this is the fast step, this is the slow step. To determine the rate law, you are only using the slow step. And that, even in terms of a concept, makes sense, right? If you say, how long is this task going to take me? The majority of the time, if you had to do two things, if you had to open the door and then walk, a mile, right? The time it takes you to do that task, opening the door and walking a mile, majority of that, at the rate that you're going to be able to do this task, for the most part, is related to the walking part, right? The part of the slower part. So that's why it's important to note that the rate law and how the rate that the reaction is going to occur is based on these slow steps. Okay, so having said that, rate law equals K, which is the rate constant, times the concentration, of the reactants to the power of either a coefficient or those, which also represents the order of the reaction. And we will go over this in a moment, but just note that down for now. So the order of the reaction is the superscript for that specific concentration. And like I said, we're going to go through an example. Okay, so let's also, before we move on, never include solids and liquids in the rate law. So if you have the chemical equation, you're taking the concentration of these reactants. If it says that one is a solid or a liquid, you're not including that substance in our rate law. So never include solids or liquids. Okay, so let's go through this practice problem to determine rate law. So rate law is down here. We're going to get to our answer, but a lot of the times you're going to get a chart like this. And let's just also note that the rate constant can be determined by any given trial. So the rate constant, if you take the rate constant, right, and you can determine that if you rearrange this equation, because you're given the rate and you're given these concentrations, and through this you can determine what the exponent will be, which I'll show you in a moment. But with that, you can determine the value of K, okay? So the rate constant can be determined by any given trial. But right now we're going to look at the rate law as a whole and how we're putting that together. And for that, you're going to normally get a table like this, and you're going to see this is the concentration. So these are the different trials, right, across. These are the different concentrations of those reactants in the reaction. So first, you're going to take you're going to need to look at your board and keep concentrations constant except for one. You're going to find one that is changing. So let's take a look at, for example, trial 1 and trial 3. Okay, I think you can see it. So for trial 1 and trial 3, So concentration of A is 0.12, here it's 0.12, and here it's 0.0, sorry, let me rephrase that. It's 0.012, 0.012, and 0.013. So for trials 1, 2, and 3, the concentration of A remains relatively constant, right? But when you get to trial 4, the concentration of A goes to 0.021. So if we are looking at, I know I said we're going to start with 1 and 3, but really we're going to start with 2 and 4. Sorry to make that confusing, but let's start with 2 and 4. So we see that concentration A was the same until you got to trial 4, and it changed. So if you take this, right, so you're looking at A to be changing. That means when you're comparing trials 2 and 4 for the B and C concentrations, those two concentrations at trials 2 and 4 need to remain constant. So let's make sure that's the case. So now we're looking at B, concentration B for trial 2. Yes, 0.102, and if we look at trial 4 for that, it's 0.104, relatively constant rate, and for C, let's look, 0.010 and 0.014, again, relatively constant. So that means that we're looking at A here. What we're going to figure out is determining based on and relative to A. Okay, so we said that if we're looking at this, right, because these B and C's concentrations stay the same during trials 2 and 4, but A's concentration changes. So if we're looking at this change in concentration, it approximately doubles, right? So from 0.012 to 0.021, that's approximately doubling, right? So when we look at that, we're saying, okay, if we double the concentration, what happens to our rate? So now we're going to look at our rate, which is our last column here, for trials 2 and 4. So for trial 2, it's 4 times 10 to the negative 5. And for trial 4, it's 8 times 10 to the negative 5. So that, right, you see a doubling of that. So we doubled the concentration, and when we doubled the concentration of A, that doubled our rate. So let me write it down here. Therefore, 2 times the concentration of A equals 2 times the rate. This means that it is a first order reaction. We're going to go over the orders a little bit later as well, but that is so important to understand. That means it's a first order reaction. This times 2 equals the rate times 2 equals first order reaction. Okay. If you multiply, you know, it's a 1-to-1 ratio, right? So if you double this, you're doubling that. Okay, so next, let's see what other trials we can look at. Okay, so let's look at trials 1 and 3 now. So for 1 and 3, we're going to look at the concentration C that is changing. So we have 0.012 for A, 0.013, relatively the same. For B, 0.092, 0.095, relatively the same. And for C's concentration, it goes from 0.011 to 0.022, which is doubling the concentration of C, right? So A's concentration and B's concentration stay the same during trials 1 and 3, but the concentration of C is doubled. So when we double the concentration of C, since those things are constant, what happens to our rate? So if we look at that, we have rate of 4 times 10 to the negative 5 and 2 times 10 to the negative 4. But in this case, let me just remind you, it's important that you have the same exponents when you're comparing these rates. So in reality, this rate down here, 2 times 10 to the negative 4, would be written as 20 times 10 to the negative 5. So we need to compare the exponents that are the same, right? So it's times 10 to the negative 5 and times 10 to the negative 5. So we need to make sure we're keeping those the same. So in that case, it's going from 4 times 10 to the negative 5 to 20 times 10 to the negative 5, right? So in that case, you're multiplying that, and you're quadrupling that, right? So if you're doubling the concentration, and you're doubling the concentration of C, and that's quadrupling the rate. That means that it is a second order reaction. The second order reaction really is anything other than if it's a 1-to-1 ratio, or if there's no effect. We're about to go over no effect, but the second order reaction is basically everything else that is not times 2, or we're about to go over the 0th order. So if it's not 0th order and it's not first order, if there's any other effect on this rate, it will be second order reaction. Okay. Next, we're going to finally look at the concentration of B. So again, if we're looking at 0.012, 0.012 for A, great. Now we're changing the concentration of B. Now this isn't a great, easy way to say, oh, this is doubling, it's quadrupling, it's tripling, anything like that. But we do see an increase, okay? So let's just take that for now. We do see an increase in concentration of B. So if we're looking at our rate and we're going from 4 times 10 to the negative 5 to 4 times 10 to the negative 5, that's the same. So even if we increase the concentration of B, there is no effect on the rate. So that means that when you increase the concentration of B, you have no effect on the rate. That is a 0th order reaction. Okay, so now let's put these things together. So we have rate, right? This was our rate law equation from above, equals K, our rate constant, times the concentration of A to the 1, because we said A relative to A, this is a first order reaction, times concentration of C to the power of 2, because we said this was a second order reaction, so 2 right up here. And we would normally include B, but because it is a 0th order reaction, that would not play a part in our rate law, right? Because you'd have concentration of B to the exponent 0. So we know that wouldn't affect this rate law here. So this is our rate law for this question. If you have any questions, I know definitely do a problem, see a couple problems, see how they're done. That's definitely how I got the hang of it. But it's much easier when you really take a minute and follow through a problem, or even replay that part of the video and really understand what I'm saying, because I tried to choose my words wisely so you can understand what was happening. Okay, so now let's look at this side of our board, which we'll go through a little quicker. So we have just a reminder, delta G equals activation energy of the forward reaction minus activation energy of the reverse. So it's the change in free energy during a reaction. So if you have a negative delta G, it means the reaction is exergonic. If we have a positive delta G, that means that is endergonic, right? So remember, exergonic is has negative free energy. It's releasing that energy, whereas endergonic is positive free energy, which means it's taking in the free energy in that reaction. So just an important concept. So next we have our Arrhenius equation, which is K equals A times E to the exponent of negative EA over R times T. So the important part of this is to recognize that the Arrhenius equation, which is K, right, is the fraction of collisions with enough energy to successfully collide. So this is going to tell you how successful this reaction is really going to be. So because we said we need all these 3 things for a reaction to occur. So this is a numerical value really showing that. So we have A, which is a frequency factor, times E to the negative EA, which like we said is activation energy, times R, divided by R, which is a constant, times temperature. So this equation, honestly, is the most important part about it is understanding the relationship of these variables. So if you decrease, for example, these things to remember, if you decrease EA, you're increasing the number of collisions, right? If you increase temperature, if this number here increases and everything else is constant, you're increasing the number of collisions. And if you increase A, you're increasing the number of collisions. And that happens because you're increasing K, because it says K equals to all of this. So if you understand the relationship of what happens if I increase this, decrease this, you can say, is the rate of this reaction going to increase or not? That's the biggest thing here. So remembering these key parts, all of these things increase collisions, which increase K, which means that the rate of the reaction is going to increase. Okay, now finally we have just a little more in depth of these order of reactions. I wanted to go through a problem first, because I know when I first saw this, I really didn't know what it meant. So for 0th order, the rate law is just going to be R equals K, right? Because R is the same even when the concentration changes. And we saw that with our example of 0th order, right? It had the B down here had no effect. Changing the concentration of B had no effect on the rate. The units for that be capital M over S. The half-life for a zeroth order reaction is concentration of A over 2 times K. For our first order, and honestly, I have seen practice questions where they have like multiple choice for a zeroth order reaction. What units are they, right? So it's like, that's why I'm just kind of throwing this information at you, because you just to be familiar with it, okay? So then we have, you might not think that's important, but as you know, the concepts and all that is important to understand, but these facts are also important as well. So we have a first order reaction, rate law equals K times concentration, right? Like we said, if you are doubling the rate, you're going to double the concentration. Or if you're tripling the rate, you're going to triple the concentration. So that direct relationship is a first order reaction. So the units for that is 1 over S, and the half-life for a first order reaction is ln times 2 over K. The second order reaction rate law is R equals K times A to with an exponent 2, and like I said, that is all others. One thing I'd like to point out, I think when I was talking about B down here, I'll have to play back the video. I think when I was talking about B down here, I said we would have had B to the exponent of 1. I'm not sure if I had said that, but what I should have said, and just to clarify in case I didn't say that, is we didn't include B here because it would have been B to the exponent 0, right? And that would have been this, our 0th order. The second order would be the rate law equals K times the concentration of A to the power of 2, and that in terms of the relationship of concentration and rate, like we said, would be all others. So it's either no effect, has a direct effect, so if you are tripling the concentration, triple reaction. If you're doubling the concentration, you double the rate. That's first order, and any other relationship is second order. The units for that is 1 over ms, and the half-life is 1 over t times A naught, the concentration of A, okay? Initial concentration of A. So that is the main thing in this chapter. The last 2 little points I'll make is that kinetic products, and I know this seems kind of arbitrary when we've been talking about this, but it's still, I've seen it appear. Kinetic products, you also see this in organic chemistry. Excuse me. Kinetic products have an increased free energy. They have faster product formation, and they are less stable. Where thermodynamic products have a lower free energy, and they are more stable, but they also are slower, they form more slowly. Okay, so that is the main things from this chapter. I hope you learned something. I hope going through this example was helpful. I know we don't usually do that, but for a concept like this, I just really wanted to tie it together. If you have any questions, please put them below as usual. And happy studying. We will see you in the next video.